Here's two more methods on how to drive the equation for a car going around an angle or going around a banked curve. And this is the equation to determine the angle that you should bank that curve. Currently, this is the most complicated problem I'm aware of in basic physics because it's like a hydra. It's like one of those animals from mythology where it's an animal, but it has several different heads. And so this equation, even though it's one equation, it has four different methods to derive it. So every time you defeat one of those heads or you think you've killed the beast, meaning that you think you completely understand this equation now, and then you can come across somebody that uses a completely different method to derive the equation, and this other method you won't understand at all, and you'll be completely lost again. So then you can learn that new method that someone shows you, and then you'll think you understand the equation again, and then you'll come across even a different way later on to derive this equation. So then you'll end up getting lost again. So that in and of itself can make this problem very confusing and difficult to learn because some of the derivations are kind of longer and more complicated. And just learning a single derivation can be actually really tough. But then you find out there's several other derivations and some of those derivations aren't even related to the method that you learned. Then yeah, it can make this problem look really confusing and almost impossible to learn. So I like to break things down. I like to take the really complicated things and break them down and make them look really simple. So that's what I'm going to do here. In the method I'm going to show, actually two methods I'm going to show in this video, we're going to pretend that this object that's traveling around a banked curve, we're going to pretend that it's actually attached to a cable, kind of like a tether ball, and it's spinning around a pole. Or you could also say it's like one of those swings at a carnival where people sit in the swings and the swings spin around and the people kind of fly up in the air. So that's going to be this video. You can see my other videos if you want to see the other methods to derive this formula. Okay, so here's the diagram. We have a angle right here. It's a banked curve. So we have a car going around this curve. Here's the angle alpha. That means this is also the angle alpha. Tan alpha equals velocity squared over radius times g, which is acceleration from gravity. So if you know the other variables, then you can solve for the variable that you don't know. I should add that the reason this equation is good to know, or the reason we would use this equation, is because if you're designing a road or a train track or something, or maybe like a NASCAR track, and you have these cars going around a curve really fast, if this curve right here isn't banked enough, then the people will tend to slide off the curve, and if you bank it too much, then they'll tend to slide down. So you want the upward force to equal the downward force. This will also give the people in the car the most comfortable ride because then they won't be pressed up against one door or another as they travel around that curve. They'll just feel a force pulling them directly down into their seats, perpendicular to the road on which they're traveling. I'm going to start out with some simpler explanations and proofs, partly because I like the idea of my channel being somewhat self-contained, meaning that if you at least understand just high school algebra, and you have watched my other videos, then you'll understand the other videos that I'm putting out. So that means you won't need a lot of outside references or watching videos from other channels to be able to understand the videos on my channel. So first off, I'm going to start out with the concept of acceleration. We just have time in seconds, 0 seconds, 1, 2, and 3 seconds. And we make a table here with the velocity. So we have the velocity of something in meters per second. At 0 seconds, it's traveling 0 meters per second. At 1 second, it goes to 10 meters per second. At 2 seconds, it goes to 20. At 3, it goes to 30. Acceleration is just change in velocity over change in time. So we have 30 meters per second divided by 3 seconds. That'll be 10 meters per second. And actually, it's 10 meters per second per second. So every second that goes by, this object will increase its velocity 10 meters per second. This second that's in the denominator, you can bring it up to the numerator, and it becomes 10 meters per second squared, which is acceleration from gravity. Technically, it's 9.8 meters per second squared, but I just rounded to 10 for simplicity. Now we understand acceleration. We can understand force. Mass times acceleration equals force. This means force over mass equals your acceleration. This means if you apply a large force to a certain mass, you'll get an increased acceleration. Or if you apply a certain force, but you have a smaller mass, then you'll have an increased acceleration because mass is in the denominator. And next page. Now we understand acceleration and force. Now we can look at the angle proofs of these triangles, and I'll explain why this is necessary. I'm going to prove that all the interior angles of a triangle will equal 180 degrees. We just draw our two parallel lines right here. We have angles alpha, beta, and gamma on top. So since this line segment right here, going from here to here, is identical to this line segment going from here to here, and this line segment going from here to here is identical to this one, they are parallel. That means this alpha has to equal this alpha. You can just, or this angle equals this angle. You can just take your pen, bring it up to there, and you can see it's the same line and the same angle. So now we know this angle of the triangle is alpha. We do the same thing with gamma right here. This line segment is the same as this line segment. This line is parallel to this line, so if this is gamma, this has to be gamma. You can just take your pen and put it down and bring it up and see it's the same line and the same angle. In geometry, I think that's some sort of parallel line theorem or something. I don't remember exactly. I'm more interested in understanding all the concepts instead of memorizing all the correct labels. Here with beta, there's another theorem that's called opposite angle theorem or something. But right here, you can imagine we have a line right here and a line right here that cross each other. You can ignore these horizontal lines, and we can just pretend that, say, this is a pair of scissors right here with a pivot right there. So when you open up the scissors, this part that opens up will be a certain angle beta. That means the part on the bottom here has to open up to the same angle beta. And thus, alpha plus beta plus gamma has to equal 180 degrees because that's a straight line. So here we move our pin up to alpha, that's a certain angle, move it over to beta, then to gamma. So all these angles have to add up to 180. So that's just what I showed here, alpha plus beta plus gamma equals 180. And inside this triangle, we also have alpha plus beta plus gamma. So it shows all these angles have to equal 180. And I'll show why we need to know this on the next page. Here is another angle proof right here. We have, let's say, a pole, and then there'll be a cable coming down and a ball or a mass hanging from that cable that can spin around. Notice this forms a triangle. So we have alpha plus beta plus 90 has to equal 180 degrees. Subtract 90 from both sides, we get alpha plus beta has to equal 90. So alpha, beta, 90. Now what we're going to do here is we have this mass hanging from a cable, and this mass is spinning around the cable. This could be like people in a swing, like at a fair or an amusement park, and it's those swings that swing around really fast, and these people fly up in the air. So here's what we need to do is make a perpendicular line to this line segment right here. I guess I could label these line segments. I think I'll do that right now. Okay, let's see if this helps. So now we know we have line segment AB is going to be perpendicular to this line segment here, which I'll call ABC, D, E. So line segment AB will be perpendicular to line segment DE. Okay, I just wrote that right here. This is how you write that in geometric terms. Line segment AB is perpendicular to DE. The reason this matters is we have our mass hanging from a cable, and this mass is spinning around like a ride at the fair. And then that will be line segment AB forming the mass on the cable. And then line segment DE, or you could say DB, is going to form the angle of our banked curve. So this will be the curve that our race car or train or whatever is traveling around. So we need to determine this angle alpha right here. So notice here, alpha plus beta plus 90 equals 180. Therefore, alpha plus beta equals 90. Therefore, 90 minus beta equals alpha. So we have 90-degree angle right here. 90 minus beta will equal alpha. And now that we know that this is alpha, then with the opposite angle theorem or something like that, I think it's called something like that, I don't know. It's like a pair of scissors that open up from here to there. If this angle opens up alpha, then that means this angle opens up alpha as well. In other words, it has to be identical. Now we know the angle of our banked curve. So now we know that this angle alpha has to be identical to this angle alpha. And we also know that this angle alpha has to be identical to this angle alpha right here. Now we know that this angle alpha is the same as this angle right here alpha. Thus, for the calculations for the angle of our banked curve, we don't actually have to even look at the banked curve angle. We can just look at the angle up here of our tether ball swinging around a pole. I should clarify here that the main point of this video, or the main derivation of this video, is that when a car is traveling around this banked curve right here, we want that upward force to be perfectly matched with the downward force. And so that way the tires and the people inside the car will not feel a force pushing them off the road one way or another. So if we want to perfectly match that upward force and that downward force, we actually don't need to look at the angle of this banked curve alpha. We can look at this angle up here as if this is an object swinging around a pole, like a tether ball. As this object swings around the pole, it'll have an outward force pulling it out. Or you could say an upward force, because as this ball gets pulled out, it also goes up. But it'll also have a downward force of gravity pulling it back down. And so if something is swinging around like a tether ball swinging around a pole, that upward force will be naturally matched to the downward force, or that outward force will be perfectly matched to the inward force. And if there were anyone traveling inside of that tether ball as it spins around, they will not feel a force pulling them one way or another. They're just going to feel a force directly down into their seats. And that's what we want the people in the car to feel. Also, I just made a note up here about the hidden math in nature. This is just one example. I think this is interesting. If you imagine the creator of the universe to give you a large blank book at the beginning of the universe, and you're supposed to write down all of the rules that govern the universe. And these rules are as they pertain to physics, geometry, laws of motion. You would think that this alpha right here, this angle alpha, would have nothing to do with this angle alpha up here, and you would think that they would just be completely two random angles that don't have to match. But for the laws of motion to work out, for an object to travel around a banked curve, this angle right here, alpha, must be identical to this angle up here. So I just think this is interesting because it's an example of the hidden laws of mathematics in nature. One thing you might be able to do to get an intuitive feel of how this angle alpha should be the same as that angle alpha right there, you can imagine this as a rigid stick right here attached to a pivot up there. And this part right here, segment ED or BD, is another stick that's attached perpendicular to the stick or the line segment AB. So as line segment AB, or as the stick swings up and down from its pivot point, you can imagine this segment right here, BD, also swinging up and down. And so when line segment AB is vertical, then that means line segment BD will be horizontal. A lot of times I found out in geometry, if you can imagine the lines actually moving or pivoting about some point, then this will help get an intuition as to how these angles will be related to each other. If you watch my video where I derive the same formula by using a free body diagram on a banked curve, then it will really help, or basically I think it'll be absolutely necessary to imagine how all of these lines will change and relate to each other as these lines pivot about some point. Because in that video there were a lot of lines and some triangles, and yeah, it could be kind of confusing. Okay, so now I've explained acceleration, I've explained force, I've proven the interior angles of a triangle, I've proven that these angles are the same. Now I'm going to go to the next page. All right, what I have here is our tether ball, or it's our mast that's hanging from a rope or a cable, and it can spin around. And by the way, I did a video on the G-forces involved if somebody's in one of those swings at a fair, so you can see that video if you want. So what we have here is the force pulling this ball down right here, and that's mass times acceleration from gravity, mg. But then also we can take this mass, be it a tether ball or whatever, a cannonball hanging from a rope or a cable or a chain, and we can actually tie another rope to it and we can pull this mass out. Now we can calculate the tension on that rope right there simply by using Pythagorean theorem of a squared plus b squared equals c squared. So to do these calculations, you can imagine tying a rope to this mass right here, and we're just pulling it out with a certain amount of force. And at the same time, there's a certain amount of force pulling down on this cable right here, that's mg. So if you know these two forces here, the force pulling out and mg pulling down, then you can calculate the tension on your rope. But also, instead of tying a rope to this mass and pulling it out, applying a force in that direction, you could also use mv squared over r equals the force, and this is the centripetal force formula. So if you know the mass of the object and the velocity that it's spinning around and the radius from the pole here to the mass, then you'll be able to calculate the centripetal force, and then you can calculate the tension on that rope. Also keep in mind, these are vectors right here, so the length of these arrows determine, or they also correlate with how much force is being applied. So this mg pushing down right here, this acceleration from gravity will always be 9.8. So whether this vector right here is really long in 9.8, or if you want to attach a rope to this mass and pull on it really hard, so it looks like this triangle right here, you will still have 9.8 pushing down right here. Thus, instead of having a vector, a horizontal vector that's almost identical to your vertical vector, you can have a vertical vector that is very small, but the number will still remain the same at 9.8, and you'll have a very long horizontal vector here for the force that's being pulled out. And thus, when you do your Pythagorean theorem of a squared plus b squared equals c squared, you will end up with a very large amount of tension on that cable. With right triangles, you don't have to use Pythagorean theorem. You could also use trigonometry. You can see the video I did on basic trig if you want to understand that. So here's the first derivation right here. This object swinging around, if these people are in a swing and this is like a carnival swing, these people are not going to feel an upward force or a downward force. They are just going to feel a force directly through their seats, pushing them straight down parallel to this cable. So what we can do is pretend that this object right here is on a banked curve, and I'll line it up just like this. There we go, just like that. So now you can see that this object is attached to a cable that's going up, but it's also on a banked curve. So the people in this car here, or this train or whatever, we don't want them to feel an upward force pushing them up this ramp or a downward force pulling them down. We want that force to be pushing directly through this cable right here. Thus, we can use the same math as this triangle right here. We can take tan alpha equals opposite over adjacent. That'll be mv squared over r because it's an object spinning around. Divide that by mg right there. Notice that mass divided by mass will cancel. They'll be gone. So we end up with tan alpha equals v squared over rg. And thus we took two objects that appear completely different from each other and have nothing in common, which is an object traveling around a banked curve and an object spinning around on a cable. And we put them together to form one formula of tan alpha equals v squared over v squared over rg. On the next page, what I'm going to do is set the upward force right here equal to the downward force. So what I'm going to do is set this line right here of mv squared over r. This will be the sine of alpha. I'm going to set that equal to the cosine of alpha. And next page. So here is the fourth way to derive it. The first two ways, like I explained earlier, were in my other videos, and that was using a free body diagram. The third method was just using the tan alpha right here. And then this fourth method, I'm going to set sine equal to cosine. So I'll say that the hypotenuse is 1, as if it's a unit circle. The upward force right here, which is also the outward force, that'll be sine of alpha. And so sine of alpha is mv squared over r divided by 1 for the hypotenuse. So that just means sine of alpha equals mv squared over 1. That is the upward force. We do the same thing with the downward force, which is cosine of alpha. That's mg over 1, which is adjacent over hypotenuse. So next step, what we do is we isolate mass for both equations. So right here for sine of alpha, I isolate mass. We end up with r sine alpha over v squared. I do the same thing here with cosine alpha. Isolate mass here, so we end up with cos alpha over g equals mass. Now I set the upward force equal to the downward force, and I will show that on the next page. Okay, so here's our upward force. So the reason we can do this is because the upward force and the downward force both equal m for mass. So the upward force right here is r sine alpha over v squared. Downward force is cos alpha over g. Then what I can do is take this cos from here, bring it down to here. Take the r and the v squared, move those to the other side of the equal sign. We end up with sine alpha over cos alpha equals v squared over rg. Sine over cos is the same thing as tangent, so we have tan alpha equals v squared over rg. Thus, now we have 4 ways to slay this hydra and have the best possible understanding of this problem. I mentioned before in my other videos, I think it's important, or at least it's really good, to know all the different possible ways to solve a problem. Because in my field where I work, I'll have learned certain equations to solve a certain problem, But then I come across one or two other people and they each learn a different method to solve the same problem. And we all only understand our own methods. We tend to not understand the other methods because they're just so different and complex, kind of like this. So if we can understand everybody else's methods, then now we know if they're right or wrong, and we have a way to double check or triple check our work by using different formulas.